Okay, let's start our webinar today. First, before I go through the details, I would like to make sure that everybody can hear me. So would you raise your hand in the GoToWebinar app so I can see that everybody hears me? Okay, good. I have gotten quite a few replies, so I think it is safe to start. Okay, so welcome everybody to this feature highlight of SimScale. Today I'm going to talk about conjugate heat transfer. We will have a look at some general aspects of conjugate heat transfer, and I will show you some examples. So everybody, whether you're familiar with conjugate heat transfer applications or not, get some sort of introduction to what we present in this feature on SimScale, and hopefully make it easier for you to do your own simulations on SimScale. Okay, so very short about myself. So my name is Babak. I'm the senior fluid mechanics engineer here at SimScale. Specifically for this project, I am the project manager. So the design of our interfaces, the kind of functionalities that we wanted to present, the workflows, all of this were under my responsibilities. But normally, I'm responsible for the fluid dynamics solvers in general and all of the related product features on SimScale. Okay, so let's start. First, a quick view on what we're going to review today. So the first thing is I will quickly show what kind of heat transfer applications we already have in SimScale. Many of you are familiar with this. I will not go through any details. It will just be somehow a short introduction so you know what kind of features the CHT is making available on top of the existing applications. Then we're going to go over CHT to see what is conjugate heat transfer. There are a few new concepts, regions and interfaces specifically, that are added. So I will try to very briefly demonstrate what these new terms are. Also, we will talk about the applications where CHT simulations are very typical of. Next, there will be a demonstration. We have made a few projects available on our community already. We will take one of them. We try to set it up together. More than a tutorial, the aim here is to show how our design has speed up the process of setting up such a complex simulation. I will go through the details during the demonstration there. Finally, I will show you some sort of homework. Maybe homework is not exactly the best term here, but the idea is to provide you with some geometry that already we know is working. We know it has all of the features that a multi-region mesh should have, and see how you guys do the simulations. In the end, there are going to be questions, so I would like to hear the questions, also your feedback, of course, but it might be better to put it for the end of the webinar. Okay. So the heat transfer in SimScale. Let's see what kind of heat transfer applications we already have available for our users. I will start with fluid dynamics. So we have two analysis types that somehow could help you do your heat transfer simulations depending on the kind of applications that you're interested in. The more complex one is a natural convective heat transfer. You'll see an example of it in this image on the left, which shows the natural convection in a light bulb. So the process of natural convection refers to the movement of the fluid due to change in its density. So we know that many of the materials change their physical properties, in this specific case, the density, when the temperature changes. So, for example, in this example of the light bulb, we see that as the filament of the bulb starts to heat up, it warms the air around it. The air that is close to the filament starts to have a smaller density Therefore, because of the gravity, it starts to go up, and of course, the whole process caused these recirculation regions that you see in the left image. There are several thermal models, so the change of the physical properties with temperature and many other properties are available in our natural convective heat transfer, but the problem is we are limited to one fluid domain. The other analysis type that we have is the passive scalar transport. Here, we are basically dealing with the evolution of a scalar field. This scalar field could be temperature, but it means that we are not considering any change of properties due to change in the temperature. So it's quite limited. It has its own applications, but it's somehow limited. Here, we also are limited to one fluid domain. You see an example of it. This is not exactly an example of evolution of a temperature field, but basically we're dealing with the same physical phenomenon. Moving forward, we also have, in fact, 4 different analysis types for solid mechanics, divided into 2 groups. We have heat transfer and we have uncoupled thermomechanical analysis. So the heat transfer, we are simulating the transformation of thermal energy between multiple solids. So one of our limitations, which was only one domain, is not present here anymore, but we are still working with solids. Of course, we also offer some advanced features on our heat transfer, so you can simulate, for example, nonlinearity in your simulations. Same applies to uncoupled thermomechanical analysis. Here, the uncoupled refers to the fact that we want to consider both structural and thermal stresses in one simulation, but what we do is that we solve for the thermal, the thermal equations, and based on those, we calculate the structural stresses. So it's not fully coupled, hence the term uncoupled, but it considers both structural and thermal stresses. Offers some advanced features as well, but still we are limited to solid domains only. Okay, with this introduction of what we already have, let's move forward to see what the new feature the conjugate heat transfer offers. Okay, so the key element in having a conjugate heat transfer, as the name suggests, is the interaction, the thermal interaction between a fluid and a solid region. This is the most basic and most important element of a conjugate heat transfer simulation. So if you want to divide it, it will be like this. In the solid regions, we are simulating the heat conduction. The heat conduction is basically the diffusion of heat due to direct contact. And in the fluid regions, we are dealing with convection of heat. This is the kind of transfer of thermal energy due to movement of the fluid elements. And of course, at the interfaces between these two regions, we have the thermal coupling. That's why the name is conjugate heat transfer, because we consider the transfer of mass and thermal energy at the same time, both in solid and fluid. Of course, we could consider other methods of heat transfer, for example, radiation. So now, now we have an understanding why what this type of simulation offers on top of the existing heat transfer applications, analysis types that we have. A few of the advantages are its accuracy and its speed. If you want to do the simulations that are of the same complexity that you typically have to simulate with a conjugate heat transfer simulation, it is extremely difficult to achieve those levels of speed because it's a coupled simulation, or accuracy because it really considers the simulated data and not some more or less simple boundary condition. It's very difficult to reach those two levels of accuracy and speed. Also, if you also see even the examples that we already put, it is very well suited for the complex scenarios. You could have assemblies. There's no limit on the number of the regions that you can use to simulate. And at the same time, there's no limit on the type of these regions. So before, I only mentioned the coupling between a fluid and a solid region, but of course you could have fluid-fluid and solid-solid interfaces as well. So all of them are treated equally. Of course, equally meaning that this analysis type could handle them. Different physics govern these kind of regions, but all of them could be put in one simulation. And the applications are really in every industry they're present. So in power plants, in electronics, in building of elements for the refineries, for example, in oil refineries, in the automotive industry, there's really it's difficult to put a limit to this list. In every of these industries that I mentioned and many more, you could find several applications where having conjugate heat transfer simulations is important. So I'll just refer to this image that you see on the right. This is the temperature distribution around the heat sink. So what we have are two elements in our domain that are solid and produce heat, and we want to see how we can cool these down with a flow of air. This is actually the simulation that later we're going to set up together. So to demonstrate how these regions and interfaces, these new terms that I just introduced in this slide form, let's have a look at this next slide. So here we see the same domain that I just presented the result in the previous slide. So what you're seeing here is the fluid domain from the outside. So you will see the inlets and outlets. We will go through the details. It's not too important to understand exactly what is happening here, but basically what we see so far is the fluid domain from the outside. So let's look through the domain now. So as you see, we see the heat sink very distinctly in the middle of the fluid domain. So the type of this heat sink is going to be solid, and it is located inside the fluid. So this is how the meaning of region is born. So in this example, the heat sink, what appears to be blue in this slide, is a solid region, and the air that is surrounding the heat sink is the fluid region. Again, moving forward, I will cut the domain and move closer to actually be able to identify the interface. So here again, we have a closer look at our sink. So the red domain here is our solid part of the domain. It represents the geometry of a sink. And the green one here represents the fluid domain, that is actually the air that runs around the heat sink. And the faces that actually are between these two domains form the interface. So at the interface, we have two faces. One of them belongs to the red domain, the solid domain, and one of them belongs to the fluid domain. We will see later that the definition of an interface actually contains putting these two faces together and defining the kind of physical properties that it has. So these are the new concepts: regions and interfaces. And of course, to connect this final image to what I explained before, here in the red region, which is a solid, we simulate the heat conduction, and in the green region, which is the fluid, we simulate the heat convection. Okay, so let's move forward to see what kind of applications are typical of CHT. As I mentioned, there's a long list. I'll mention quite a few, and hopefully over time we have many examples of these in our community. So the first thing that we already saw was the cooling of electronic devices. So these devices typically produce heat, and of course the performance is a function of this the temperature that they have. So the manufacturers have to define certain methods to cool down these devices, and this is basically what cooling of electronic devices is about. Another very typical example are heat exchangers. We see an example that we simulated earlier on the right, on the image on the right. So in this heat exchanger, what happens is that we have a fluid that, due to some process, has a higher temperature, and we want to cool it down. What we're interested in specifically in this example, we don't want to mix these two fluids, the fluid that has to cool down with the fluid that actually acts as the absorbing fluid. So what happens is that we enter, in this example, for example, water from one side of our heat exchanger, and run air through the outer chamber across the flow of the water. They don't mix because they're in different fluid regions, but they're connected through pipes which represent our solid region. As you see, on the right of this heat exchanger, the air enters, runs over the pipes, gains some heat, and as it leaves the heat exchanger, it already has a higher temperature. The color here represents the temperature. So heat exchangers are also a very typical example of CHT applications. Then we have HVAC. In all of the different applications of HVAC, we have several examples of CHT simulations. Combustors and burners, this is also a more specialized topic, but also a very common application for conjugate heat transfers. Another example is gas turbine design. For example, the cooling of the blades, because there are really different mechanisms to cool down the blades. For example, one of them could be internal cooling. There is a very common case where actually, running a simulation with the coupled solver, with the CHT solver, is common. Also, cooling of the engine due to both the heat that the engine puts out, also its efficiency. Analysis of cooling of an engine also is very, very common. And it also could go to very smaller applications like home appliances. To make sure something that is going to be used in an environment of a home have enough isolation, so for example the temperature at its outer surface is not exceeding certain limits. Okay, so with this we should have already covered the applications of the CHT, the new terms that already are introduced, and really what the CHT is all about. To move forward, I would like to set up a simulation on our platform now. I'll first show you what we're going to do, what the application is, and then I'll switch to the platform. So on the left here, you see our geometry. The same view as we saw before. The inlets and outlets are clear. So what is going to happen is that normally there is a fan inside that sucks the air through the inlets, and there's an outlet that blows the air, from those. If you look at the bottom of our geometry, we see two regions that have a different color. These are our two solid elements, our electronic chips that produce the heat. So we want to see how the flow of the air that we create through this inlet and outlet enhances the cooling of these two elements. As you will also see, on one of the chips we have installed a heat sink that should enhance the transfer of heat from the heat-producing element to the air. All right, so let's go here to the project. This is the geometry. I hope everybody could see this. This is the geometry that that I just mentioned. I'll directly just open it and go through the setup. Okay, so the first step is to make sure we have a correct mesh. So there is one very important difference between the kind of meshes that so far we had for our fluid dynamic solvers and the kind of mesh that we should use for conjugate heat transfer. As I mentioned, there's no limit on the number of regions that that we can simulate. Therefore, the geometry that we upload could have several solids. So far, it was only one solid. So this is the main difference. As you see, we have, in this case, 4 solids. I'll just hide this one on the outer, so you see the other 3 on the inside. So here is one of the heat-producing elements. Here we have the heat sink, and it's at its bottom. Maybe I can show it to you. Yep. Here we have the other element. So this is our geometry. The mesh, a multi-region mesh, is created using the hex dominant parametric mesh. So you have to choose this, and you have to make sure that you have true here for create multi-region mesh. This property actually tells the mesher to create one separate mesh for each region and create an interface between them. So it's very important to make sure you have this one as true. If you have it as false, you're going to have a normal mesh like we had before, and if you try to do a simulation, the CHT simulation with that mesh, your simulation is going to fail because the mesh is not valid. One also very tiny hint, of course you can find these all on our documentation. If you want to refine your regions because their size is small, or for example for the fluid elements, you want to make sure to capture the thermal boundary layer when you're close to the surface of the solid. Therefore, you might want to define some additional refinements. This is done by creating a refinement as we did before. Maybe I'll also show that to you here. So, so if you scroll down here, you can, as before, add mesh refinements. You can click on Add Mesh Refinement and then choose a surface refinement. You can define a maximum and minimum of the refinements you want to create, and then you have to create a cell zone. This cell zone is later going to translate into a region for our CHT simulation. So when you select true here, you will give it a name, and that's all you need to do. Once you assign it to one of your solids, that solid is going to be a region for your future simulation. If you do not define any of these mesh refinements, you automatically, when you select true here, you automatically create one region per solid that you have created. So it still is a valid mesh for a CHT simulation, but you have to make sure that the size of the mesh is capable of capturing the kind of physics you want. So really, defining further refinements is about capturing a quality simulation, all of the physical phenomena. Okay, now we have a mesh. Let's move forward to setting up a simulation. So I will start by creating a new simulation. Next, I will go to fluid dynamics, and as you see, we have the conjugate heat transfer analysis type. In this case, we're going to do a steady state laminar simulation. I'll do my setup here, save, and now you see on the left we have the tree. I'll assign the multi-region mesh that is created. I'll save it, and already one of the elements that is new to this for this analysis type appears, interfaces. So let's add an interface and see how it works. So I'll add interface connection. If you scroll down, you will see an interface is defined by having at least two faces. As I mentioned before, one face belongs to one of the regions and the other face belongs to the other region. So at their interface, at the place where they actually touch, we have two faces. We connect the two faces like this through definition of an interface. Here we have the properties of the interface. We can define what kind of thermal coupling this interface is going to have and what kind of momentum coupling is going to have. Momentum coupling is basically similar to creating a velocity boundary condition. Typically when we have an interface between a fluid and a solid region, we are dealing with a no-slip coupling. Therefore, this is the default setup. And for the thermal, we also have two options. The coupled means that the exchange of the heat at this interface between the two regions is allowed. And the solver automatically takes care of the details here. And the adiabatic actually means that there's no exchange of the heat in here. For example, if you want to have an insulator in that interface, this is how you can define the interface. So our default options are no slip and coupled, and this is also our automatic interface. So if you know that in your application all of the interfaces have this no slip plus coupled kind of interface, you basically do not need to create any interfaces. Of course, it is safer to do that and make sure you have all of the setup defined and checked by yourself. But this is one of the features that speeds up the process of setting up a simulation greatly. So for now, I will create maybe one or two of the interfaces so you know how it works, and then I move forward. So here I want to create an interface between the fluid domain and our solid zero. If you remember, this solid 0 is this chip. So I will create an interface between this face and the corresponding face of the fluid. So what I will do is that now I can pick a face, I click here, and then I add the assignment to my widget here. So this face is, the name is, as you see at the bottom of the page, solid 0 to fluid. That's why I choose from here. And I will do the same at the bottom here. So let me change the face. I've selected it here. I click, that's where it appears. And I will also should assign its conjugate, which is, in this case, this was solid 0 to fluid. So I have to choose fluid to solid 0 as its pair. So this is how we define an interface. One face here, one face there, the properties here. Maybe I can also give it a name, then I'll save it, and that's how we have it here, connection 1. So in this case, if you wanted to define all of the interfaces, this would be one of them between the fluid and one of the chips, then another between the fluid and the sink, and a third one between the sink and the chip that is at its bottom. This third one is a solid by solid interface. The good thing is you do not necessarily have to define it here. When we are taking the case to run it, we automatically convert detect these features and write the appropriate input files for the solver. So this is how we define a connection. Moving forward, here is the information about the mesh, nothing new, and here we have the gravity. Just make sure that you define the gravity. Of course, if the application is doesn't require gravity, then you're fine, but for most of the applications you need. Here I did this because it was in the negative y direction, and the gravity is set. Finally, we get to materials. This is where actually we define the type of each region. First, let's add a fluid material. As I mentioned, the air enters from these inlets and leaves from the outlet here. So what I will do is to go to the library, choose air, and select it. Assign it to the fluid zone, and that's how you create the air as a region. So here we have under fluid we have air, and we know we don't need any more fluid material, so I move forward to solid. I add a solid material. Let's say we want to have, for example, copper. Okay, and if you see now, you only see solid material. So it also, gives you a lot of options. At the same time, it separates them, so you don't need to worry about them mixing. So I choose the copper, save, and I assign it to for example, this solid 2. To the two of the solids here. This would be my second material. I want to add a third one. So you see, you can add, in this case, maybe aluminum, and that's it. I will assign it to this, and this is our complete material setup. So you see the list of the materials categorized by fluid and solid already here. Okay. The initial conditions, very similar to before. What we have new is that you can define subdomains for the temperature. I'll show you why this is important. So in this case, let's say we want to say those two elements that produce heat initially are at a higher temperature. So what I will do is to say that everywhere in the domain we have this temperature, but I want to add a subdomain. I add a subdomain. I choose those two elements that are going to be hotter. In this case, it would be these two, and I give it a higher temperature. That's it. So I gave it 363 kelvins. I assign it to those two domains, and that's it. So initially, they're going to have a higher temperature. Same applies to the boundary conditions. This is very similar to what we had before, nothing new here. Some adjustments are made, and some of the features are, again, like before, automatically captured once you are done with your simulation. So even though the type of boundary conditions that you have to set up for a CHT simulation are somehow different or have different properties, we have managed to design this feature in a way that you do not really need to deal with many of these complexities. So this is again the same as before. As you see, we have all of the types that we had before, and I will not go through this since it's really similar to what we did previously. Numerics also the same. We have, as you expect, because the simulation is more complex, we have a long list of numerical schemes, but we've tried to change the default values to something that is going to increase the chance of your simulation to successfully finish. Also, we sometimes adjust these values according to the specific kind of application. For example, if it's a steady state or a transient, or if you're using turbulent modeling, to make sure the simulation has the highest chance of succeeding. So this is the same as before. Also, simulation control, all of the features are the same as what we had before, and that is it. We are close here. We can create the simulation. Let me just assign this to something so it does not complain. And yeah, that's it. The familiar warning that not all of the boundary conditions, not all of the faces of the geometry have boundary conditions, but you know, if you're sure, the rest of the boundary conditions are the ones that we produce by default, which is an adiabatic no slip wall. You don't need to create them. Just say OK and create a new run. And that's it. Okay, so now together we created one complete CHT simulation, and given the complexity of this kind of simulation, spending only 5-10 minutes to set it up is really quick. And this is one of the most important factors that we had in mind when we were designing this analysis type. To be able to very quickly move from a geometry to the results, not having to spend a lot of time on identifying the interfaces, identifying the regions, because as the number of the regions increase, it could become very complex. Okay, so this was the demonstration. Let's go back to our slides. And now it's time for the homework. So what we had in mind was to, now that you have, we've had an introduction to the CHT, prepare a geometry for you and give you guys the chance to do your simulations on this geometry and somehow present it in the community. So first let me show you the geometry and then tell you how we're planning to proceed. So this is the geometry that we have prepared for you. It's somehow similar to the demonstration case for the heatsink that we saw. Let me show the project to you on the platform. So here is the project. We will add a link to the project to the webinar page, so you can also land on this page. Of course, you know how to make a copy for yourself and do your simulations there. So I would suggest use that link, or maybe just search for tutorial CHT to get this project, make a copy for yourself, and move on with the creating the mesh and the simulation. So for you to know what kind of details you need to set in this simulation, we have created a page in the forum. You can find the link, as you saw, at the bottom of the project page. And here is the step-by-step tutorial how to set up this case. So as you see, and thanks Ali for this very nice tutorial. We start from here. It takes you through the meshing, and I'm sure you can create a very nice mesh using these instructions. So at the top we have the up to here we have the steps to create a mesh, a multi-region mesh. Moving down here we have the simulation setup, basically the same thing that we went through to have a final simulation. So I would suggest let's make a copy of this project, do the simulation, and maybe add a tag, something like my first CHT project or my CHT project, something similar along these lines that you prefer, to the project description. So it would be here at the project description. and until Friday. And on Friday, we will publish the complete simulation according to the tutorial, to these instructions that I just showed you, and we can compare our results to see if the results match, maybe even study the impact of the numerical schemes, the type of the boundary conditions, everything, and see how the results match with each other. Again, we add the link to this page, to the webinar page, so it will make it easy for you to access the project. Yes, and this was all I wanted to talk about today about our CHT feature. This was a feature that was requested by many of our users and customers, so I hope that you guys find it useful. I'm sure there are so many features made available for you that is going to be helpful for you to do your simulations. Okay, so now I would like to hear your questions. If anybody has questions, let's hear it. Maybe raise your hand and or maybe write the question in the chat, and then I'll go over them and answer them here for you. Okay, I have one question. This is regarding the type of the mechanisms of heat transfer that is available. As I mentioned, exactly, the question refers to radiation. As I mentioned, we have conduction in the solid, we have convection of the heat in the fluid, and I mentioned that radiation is also one of the ways. So in the current feature that we have made available, radiation is turned off by default, but it is possible to add it very easily to the simulation. So to give a concrete answer to the question, radiation is not possible at the moment, but is going to be added with several different models very soon to both conjugate heat transfer and natural convection. Okay, I have a question about the automatic interface setup. Sure. I will go back to the project to show you what the automatic interface setup was about. So here again, this was the setup of an interface. As I mentioned, the interface means the coupling of two faces. So the idea is that if the number of regions increase, you will see that the number of interfaces between them is going to increase very rapidly. And this makes the setup of the simulation very difficult because it takes a lot of time, and also it leaves a lot of room for error. That's why we added, on top of the manual setup that normally our users have, we added an automatic detection of the interfaces. So the feature looks for the interfaces based on different conditions, and as soon as it identifies one, if that interface is not already defined by the user, it assumes that based on the type of the regions that it assumes a certain type. For example, if it's an interface between a fluid and a solid, it assumes that the thermal coupling, as you see here, is set to coupled, and the momentum coupling is set to no slip. So basically something that is typical of many of the fluid-solid interfaces. Same applies for fluid interfaces where we have slip, and solid-solid where the momentum coupling is not relevant. This is how we have automatic interface. Okay. I have a question. How can I have a look at the results on the project that I just showed? I will show you how to do that. If you go to our public project, so the project that I just showed was simply for the demonstration. But here at the top, you will see heatsink electronics cooling using CHT. So I'll click on it. I will go inside. You'll see we have a very nice description of the project, also along with the explanation of the geometry and the simulation. And we also have some post-processing steps. If you open the project, you can go to our post processor and actually do the complete post-processing of the data online. As you know, now we have more capabilities in our post-processor. So if you take this last run that we have here, this successful run, and open it in the post-processor, you can actually do the complete post-processing of the data. I will show you a couple of screenshots that we've created for a little more, for a project that is a little more complex. I'll really invite you to actually use this post-processor. So here's the other project, the heat exchanger, that we saw a screenshot of it. If you scroll down, you will see that all of these, of course not the text here, but all of these are created with our online post-processor. So yeah, you can use the online post-processor. I have a question. Does SimScale generate contacts between solids? I'm not sure if how can I answer this accurately here. We have this feature in the pipeline, but maybe this could be checked with our support to see if it already is available, or if the situation is different. Okay, I have a question. How do I add an adiabatic external boundary condition to a solid? So as you saw, we divided the boundary conditions into two parts. We have interfaces, which are between two regions, and we have boundary conditions. So you basically have to do the same as you did before. In this case, if you want to have an adiabatic, meaning no exchange of thermal energy, for the temperature you have to choose a zero gradient condition. That ensures that no heat is lost from the boundary condition. If you go through the kind of boundary conditions we have for temperature, you will find a few other boundary conditions that are more complex and give you more possibilities to assign as an external BC. Okay, we also have a question. Would it be possible to simulate the solid with a thermal output instead of a given temperature? Of course. So what you can do, this also is covered under those boundary conditions. You can create a boundary condition that generates heat at a certain rate. This is how you do it. We have a question about turbulence models. What kind of turbulence models is recommended for a steady state CHT simulation, for a steady state turbulent CHT simulation? I would say it depends on your application. So we have both RANS and LES models. You really have to see what kind of phenomena are you dealing with. Are you dealing with a highly turbulent flow with transient effects? If that is the case, you have to go with an LES simulation. It's more expensive, of course, but it really, up to a certain scale, it resolves the turbulent behavior. If the level of turbulence is not that high, you could use the RANS models, which we have actually K omega, SST, and K epsilon. These two are already offered. There's a question, can a transient heat flux be included in the CHT boundaries? If I'm understanding this correctly, you're asking whether we can define a value that changes over time or maybe in the course of the simulation. That is in principle possible, but it falls under the same input way as we have with CSV files and with functions. To be honest, I'm not sure if it's already available for heat flux or if we should add it. But based on this answer, I would say it's if it's not there, it's very easy to add. I suggest to get in touch with our support, and if it wasn't there, I think they could give you more information. Okay, so it seems that all of the questions, or at least the ones that were not redundant, are answered. So here I would like to conclude this webinar. I hope that everybody uses this feature on our platform and find it useful. As I mentioned before, this is not all of the features that we're going to put out in terms of CHT. Many additions in terms of features, in terms of capabilities are going to be added over time. So I really encourage you to use this, and also let us know what you think, give us feedback, and of course post your interesting simulations. Okay, then I would like to thank everyone and say goodbye at this point.